Hey, it's Horner, and this is 1997 Mechanics number 2. You have an open top railroad car, so you can see the railroad car, and there's sand that's dumped into it. Um, when the car is under that conveyor, that sand is dispensed, just a narrow stream, and it comes out at a steady rate. So it's the change in mass divided by the change in time, and they make that ratio C. And it falls vertically from an average height of h above the floor of the railroad car. The car has an initial speed of VO, and the sand filling it is from time t0 to time is equal to capital T. So they want us to express our answers in terms of all those given quantities and the value for gravity, which is g. So here it says determine the mass of the car plus the sand that it catches as a function of time. So we can just say that that mass is equal to the original mass plus, and then we have delta m over delta t. That's for the sand that's falling in times time. And we know that delta m over delta t is equal to c, so we can just substitute that in. So that's m is equal to mo plus capital C times d. And that's all there is to that first part. So this is worth 1 point here, and this is also worth 1 point here. For the second part, they want us to determine the speed of the car as a function of time, going from 0 to little t to that capital T itself. So for this one, we're going to use the conservation of momentum. We know that the original velocity, original mass times that original velocity is equal to the final mass times the final velocity. So we're going to substitute into this expression what we had in the previous. So we know that MO times VO is equal to, and then for the mass here, we're going to put MO plus ct times that velocity. And then the correct answer, you've got to solve for this velocity or they won't give you all the points. So here v is equal to MOVO, and that's divided by MO plus c times t. For the next part of this problem for letter C, it says determine the initial kinetic energy, Ki, of the empty car. And so this is really easy. We're just going to use our kinetic energy equation. So we know that the original kinetic energy, Ki, is equal to the original mass times the original speed squared, all divided by 2, or 1/2 mv squared. They then want us to determine the final kinetic energy of the car, Kf, of the car and its load. So we know that the final kinetic energy should be equal to m, so that's the final mass, times v squared divided by 2, that's just 1/2 mv squared. We also know that little t is equal to big T, so here we're going to say Kf. Now we need to substitute in, so big M was big MO plus C, which is that ratio, times, and now we've got to have big T here, because that's the time afterwards, divided by 2, and then we're going to put in what we had for velocity, which was MOVO, so that's the original velocity, divided by the original mass plus that same thing again, C times T, and we can square it. If you want to, you could also then go ahead here and rearrange some things, and you could say this is Kf is equal to MO squared times VO squared. We just went through and did that. We also can cross off this MO plus CT, and then we divide that by 2 times MO plus CT. And by crossing off this CT, notice that we still have an MO plus CT on the bottom because of the square. The next part wants to know, is kinetic energy conserved? And then they want to know why or why not. Obviously, kinetic energy is not conserved in this. It is not conserved, and it's because this is an inelastic collision. Next thing they want us to do is determine expressions for the normal force exerted on the car by the tracks at the following times. So this is before TO, this is when it doesn't really have anything in it at all. When it doesn't have anything in it, we know that we just have our car. So here's our car, and coming straight down is mg. And then we know that going straight up here is going to be n. And remember, we called the original mass of this mo. So for this one, we can just say that n is equal to mog. For the next time, this is the weight of the car plus the weight of the sand that's accumulated in the car plus the force required to stop the vertical motion of the sand, because there's a little bit of that when it hits the car. So what we'll do is we're going to say that's N is equal to MOG plus, now this is the weight of the sand plus the force of the sand that we need to stop because that sand is falling. The correct expression for the weight of the sand would be the weight of the sand is equal to, remember we talked about that ratio, times time. That'll give us mass, and then we multiply that times gravity, because remember C was equal to delta M over delta T. And if you multiply that times T, you can cross off the T's. Now we've got M and G, and that mg would be the weight, and that's what we have here. For calculating the force of the sand in terms of the sand's change in momentum. So remember here, delta P, change in momentum, is also equal to J, which is impulse, and that's equal to force times time. So we're going to use that down here, but we're going to say force is equal to the change in momentum over the change in time. Change in momentum is delta mv, and that's v in the y. That's the speed in the y, so that's the speed of the sand as it falls, divided by the change in time. And that's equal to, now remember m over delta t is c times vy. So to find vy, we can either do kinematic equations or we can use conservation of energy. I think it's probably easier to do conservation of energy, so we're going to say 1/2 mvy squared is equal to mgh. Since the sand is falling, we know the potential energy at the top should be equal to the kinetic energy at the bottom. So this now becomes Vy is equal to the square root of 2 times GH. Notice your masses cancel. And then the complete expression is going to be N is equal to, now we need to put in our our MO here. I'm sorry, yeah, our MO. So it's MO times plus CT. MO plus, I'm sorry, so MO plus CT. And we multiply that times gravity, and then we need to add that to C times the square root of 2 times G times H, and that is our expression for the normal force here exerted on the car by the tracks at the following times. And then finally, the last one they want us to do is to figure out, for letter D, the normal force here after T is equal to T. So it's really just the car plus the accumulated sand. So this would be N is equal to MO, that's the original mass, plus CT times G. And that is the end of this problem.